today we will use this overhead projector like this and come back to that lecture and see how it progresses. Okay. Do you have any questions? Okay, there was a question raised last time. This is regarding the two solutions that we had obtained for when we tried to solve the problem for complete conversion. That means essentially assuming that E2 also changes with Z. So let me recall those equations. We had actually derived three equations. Let me write those three equations. du1 by dz is equal to minus kappa u1 u2 sin theta. du2 by dz is equal to kappa u1 square sin theta. And we had also obtained u1 square u2 cos theta is equal to constant, some constant c. So that means as the waves progress, u1 is the amplitude of the electric field at frequency omega, u2 is the electric field amplitude of the electric field at 2 omega, and cos theta was defined as phi 2 minus 2 phi 1. And so E1 was written as u1 e to the power I phi 1, and E2 was written as u2 exponential I phi 2. So there is no approximation in these equations. We are assuming there is interaction between omega and 2 omega only. Now, what we said was, for example, first situation is when I have only the fundamental wave incident on the crystal, which means that I have a situation where you have the crystal here and you have omega incident. So the condition you immediately get is u2 of 0 is equal to 0. There is no second harmonic incident. So this implies, from this equation, this immediately implies c is equal to 0. The constant is equal to 0. So we said that this particular equation now implies, because u1 and u2 are not necessarily 0 as z changes, cos theta must remain 0. That means theta must be plus or minus pi by 2. Because c is a constant independent of z, constant of motion. So as z changes, as the waves propagate, u1 and u2 change, but theta will remain such that c remains 0. Theta will remain as plus or minus pi by 2. Now, let us look at which of these solutions will work out. The first thing is, suppose I assume theta is equal to plus pi by 2, which is what we did in the class earlier. So if theta is equal to plus pi by 2, then you look at this equation. du1 by dz is minus kappa u1 u2, and du2 by dz is equal to plus kappa u1 square. And so du1 by dz is negative and du2 by dz is positive, which means that from z is equal to 0, the fundamental wave will go down in amplitude and the second harmonic will increase. du2 by dz is positive, so u2 will increase with z and u1 will decrease with z. If I choose the other value of minus pi by 2, you will get du1 by dz as plus kappa u1 u2, and du2 by dz will become minus kappa u1 square. Now, because you have not incident any second harmonic, this solution will not work. So theta automatically becomes plus pi by 2. All I am doing is I am incident with a wave at omega frequency. The second harmonic gets generated within the crystal. The phase of the second harmonic will be such that it is phi 2 minus 2 phi 1 is equal to plus pi by 2 automatically. Because the minus pi by 2 gives me a wrong solution. With the minus pi by 2, I would have to decrease u2, and u2 is already 0. U2 is the amplitude, the phase is contained in phi 2. So this second solution, theta is equal to minus pi by 2, is not an allowed solution in this problem. And when the waves enter, when the omega frequency enters and propagates through the crystal, automatically the second harmonic gets generated with a phase of satisfying phi 2 minus 2, phi 1 0 plus phi by 2. Does that answer your question?
Sir, one more doubt.
Yeah.
Actually, sir, it is at the boundary.
Yes.
So at the later stage, also theta is equal to pi by 2.
Yes.
But sir, I mean, at the later stage, there will be both the harmonics.
Yes.
So how is it remembering that the earlier at the current position? So why is it has to take care of what was at the boundary? I mean, at the current position, there are both the waves. So why doesn't it work out with both?
No. So theta is fixed to be plus pi by 2 because of my constant of motion. Because my constant of motion says u1 square u2 cos theta must be a constant. So because I started with u2 is equal to 0, at z is equal to 0, c is 0. The moment c becomes 0, at z is equal to 0, it has to maintain that z is equal to c is equal to 0 always. Because this coefficient u1 square u2 cos theta is independent of z. This is what I showed you. So because u1 and u2 are functions of z, the only way I can have this as a constant of motion is theta becomes plus pi by 2 or minus pi by 2 automatically. Now the minus pi by 2 solution is not allowed. So it becomes plus pi by 2 and it maintains plus pi by 2. The phase at which the second harmonic gets generated is automatically chosen by the interaction process such that phi 2 minus 2 phi 1 remains plus pi by 2 as the waves propagate. Now, because as I showed you, if I solve these two equations simultaneously, I will never reach a situation when u1 becomes 0. Because u2 increases as tan hyperbolic function. And the tan hyperbolic function will never become 1. It asymptotically tends to plus 1. So I will never reach a situation where all the fundamental gets converted to second harmonic. Even if I have perfect phase match operation. So as far as second harmonic generation from fundamental is concerned, the phase of the second harmonic automatically gets fixed at plus pi by 2. The generation is such that the second harmonic phi 2 becomes phi 2 minus 2 phi 1 is equal to plus pi by 2. It's fixed by the interaction process.
Here we are saying that it becomes constant as pi by 2.
Yes.
So can we use this system as a memory system? I mean, it is remembering that pi by 2 is maintained.
Yes. No, memory means the phase difference between these two will always remain plus pi by 2 as the waves propagate. It doesn't change from plus pi by 2 always. If you start with 0 second harmonic with only the fundamental incident, theta is always plus pi by 2. Now, if I look at the other situation where I look at the amplification process. So here I have not just omega incident, but I have a strong 2 omega incident and a weak omega incident. So I have a strong 2 omega and a weak omega. Remember, the problem we started looking was, can I generate omega from 2 omega? And I showed you that, in fact, if you look at these equations, you can show that if your u2 is finite and u1 is 0 at z equals 0, u1 always remains 0, as I showed you from those first equations. Now, because I am incident both omega and 2 omega, at z is equal to 0, u1 square u2 cos theta is some value, depending on the value of u1 and u2 and theta, as I choose. But if I choose, so now I have a choice of theta. If I choose theta to be such that phi 2 minus 2 phi 1 is minus pi by 2, if I choose the condition that theta is minus pi by 2, then I get an equation du1 by dz is equal to plus kappa u1 u2 and du2 by dz is equal to minus kappa u1 square. In this case, the power of the second harmonic will decrease because du2 by dz is negative and du1 by dz is positive, so the fundamental frequency will get amplified. Now I have a choice of theta, because at the input I can choose theta is equal to minus pi by 2, c becomes 0, c is maintained at 0, and so theta becomes minus pi by 2, so sin theta becomes minus 1, and I get positive du1 by dz and negative du2 by dz. So the omega frequency will get amplified if I choose this particular phase. If I choose the phase theta is equal to plus pi by 2, then I will have a power flow from omega to omega. So depending on the choice of my theta at the input, I can have an amplifier of omega or an attenuator of omega. I can convert omega to omega or to omega depending on the value of theta I choose at the input. And this is what I meant by saying that this is a phase sensitive amplifier. Whether the omega frequency gets amplified or not depends on the phase of omega, which is if I fix a value of phi 2, as I change my phi 1, whenever phi 2 minus 2 phi 1 is minus pi by 2, I will have amplification, and whenever phi 2 minus 2 phi 1 is plus pi by 2, I will have attenuation of the omega frequency. So this is what I showed you the other day, a slide showing that I can actually change the phase of phi 1 with respect to phi 2 and show experimentally that whenever this quantity becomes minus pi by 2, I have an amplification, and whenever there is a plus pi by 2, I have an attenuation of the omega beam. So that's a very interesting amplifier. It's a phase sensitive amplifier, and as I mentioned to you, we will later on discuss some quantum properties of this amplifier because it has very interesting quantum features in terms of noise of this amplifier vis-a-vis an amplifier which works on population inversion principle, which is a typical amplifier that is used in lasers. So this is essentially the parametric amplification problem. So let me try to look at an example and calculate what kind of amplification do I get. What is the kind of gain? So if you take, for example, situation with theta as minus pi by 2, this is the equation I get for u1 and u2. If I assume no pump depletion, that means if I assume 2 omega is very strong and the amount of power lost from 2 omega is very small, I can assume u2 to be a constant, integrate this equation. So I will have du1 by u1 is equal to kappa u2 dz, implying u1 of z is equal to u1 of 0 into exponential kappa u2z. You can integrate this equation and get the solution as u1 of z is u1 of 0 exponential kappa u2z. What is u2? u2 is the amplitude of the electric field at the second harmonic at the input, which does not change in the approximation we are looking at, and kappa is the coupling coefficient which we had omega d by Cn1, which is also equal to omega d by Cn2, because we are assuming phase matching. We are assuming phase matching under which we have written these two equations, delta k is equal to 0. So what will be the power gain coefficient of the frequency omega? Gain coefficient of in terms of power. This is amplitude, remember. So you have a gain coefficient if you have exponential gamma z. Gamma will be the gain coefficient. So in terms of power, what will be the gain coefficient? 2 kappa times u2. Because this is amplitude, the intensity will go as square of u1. So it will be exponential 2 kappa u2 z. So the gain coefficient is equal to 2 kappa u2. So let me substitute in this equation 2 times omega d by Cn1. Now for u2, let me write this equation. P2 is equal to n2 by 2c mu 0 mod E2 square into area of cross section of the beam, intensity multiplied by area of cross section. This is equal to n2 by 2c mu 0 u2 square into area. So this implies U2 is equal to square root of 2c mu 0 P2 by so the gain coefficient becomes this multiplied by this expression for U2, which is square root of 2c mu 0 P2 by this is N1 because N2 is equal to N1. So it depends on nonlinear coefficient D. It depends on the power at the second harmonic. It is the presence of the second harmonic 2 omega wave which is actually leading to this amplification. I am converting from 2 omega to omega. So as I mentioned, this process is that what is happening here is this 2 omega photon and the omega photons interact, and this omega photon stimulates a 2 omega photon to down convert to 2 omega photons. If I did not have this, if I had only 2 omega input, classically I do not generate omega. But quantum mechanically, this is an allowed process. 2 omega getting converted to omega is an allowed process. Just the reverse of omega getting converted to omega. So that process is a spontaneous process and it's called spontaneous parametric down conversion. In the presence of omega, this omega light can induce this down conversion, which classically these equations predict, and this is something like a stimulated parametric down conversion process. So in the presence of this omega photon, these 2 omega photons are actually splitting and generating new omega photons. And it is exactly like the stimulated emission process where there is complete phase coherence between the generated omega photons and the incident omega photons. It's a phase coherent amplification. The spontaneous process is spontaneous because there's nothing else to induce the emission process, and so that's a spontaneous parametric down conversion. And here it is a stimulated parametric down conversion process where the omega photons interact with 2 omega photons, inducing the 2 omega photons to split into omega photons. And so that is the reason why the power in the fundamental wave is increasing with Z. The electric field of the omega frequency is increasing exponentially with Z. Yeah, Mohit.
Sir, do we have to induce this omega frequency?
When you are incident in the crystal, the presence of the omega photon along with the 2 omega photon induces this down conversion process automatically. That's contained in those equations.
But omega is already present there, or it has to be artificially?
I'm incident from here.
We have to do it.
Yeah, if I don't put this, then I have to have a spontaneous parametric down conversion process, which classical equations do not predict. If I input omega also along with 2 omega, then the classical equations predict an amplification process, then it's consistent with quantum analysis, and this process is essentially an induced process. It's like a simulated emission process in a laser.
But this process won't be continuous.
It will be continuous because there is omega is continuously input.
So, but the phase difference between the two can be maintained?
Yeah, if I maintain. If I change it, obviously it will change.
It's not possible to maintain it.
It's possible. It's possible. Because the technology is advancing. In fact, what people do to demonstrate this is I start from an omega, go to 2 omega, don't convert all the omega into 2 omega, and then I mix the 2 omega and omega and amplify the omega. And I change the phase between the omega and 2 omega waves from outside. So I can actually show this amplification process, and to maintain the phase difference is not very simple. To maintain it at theta is equal to plus pi by 2 or minus pi by 2 constantly.
So the amplification keeps on being done as the wave propagates through the crystal.
Yeah.
So let's say from some part of the energy is converted from 2 omega to omega.
Yeah.
The light is generated at omega frequency. So is it also in the same phase condition as?
Yeah, classically the electric field simply increases in amplitude. So you cannot identify at the output which was the wave which was incident and which is the wave generated in the crystal. This is right now no photons, it is classical waves, right? So the waves are incident, the wave is incident with a certain amplitude, the wave comes out with a larger amplitude. What portion of this was incident and what was generated, I have no way of finding out, because it is just increase in amplitude, just like a simulated emission process. In photon picture it becomes a little more trickier, because I have to then define what is the phase of a photon. That's very tricky. Okay, so right now the photon picture I am just bringing in to show you that actually quantum mechanically it is the omega is getting amplified because the 2 omega photons are splitting and generating omega.
But experimentally, in reality, we do not need a pump, or we do not need a seed omega frequency rate. We could just send a 2 omega and we would get a omega, but because it is quantum mechanically allowed.
Yes, you will get omega, which is spontaneous parametric fluorescence, but intensities will be very weak. If this process has certain efficiency, we will calculate these numbers a little later, and the efficiencies are very poor. The efficiencies, the emission probability is as if you had one photon incident at omega. How much of photons will it generate? That will be what you will get in a spontaneous process. Here I am doing, what I am doing is, if I put even very little, 1 nanowatt of power at omega frequency, there are enough number of photons. Huge number of photons are coming in, and this process amplifies. So as an amplifier, it's interesting because I can amplify any frequency omega. All I need is a crystal and a wave at a different frequency, at a higher frequency. As I told you, this is called degenerate case, where this is half this frequency. That means 2 omega splits into 2 omega photons. But later on, just after finishing this, what we will look at is when I have an incident photon splitting into 2 photons of lower frequencies. They need not have the same frequencies.
And physically, when we perform the experiment,
yeah,
so both the beams have to be aligned on the same spot.
In the same direction of propagation, because that is the direction where I am phase matching.
No, direction is like, it can be spatially apart also.
No, they cannot be. They have to be overlapping, because otherwise, if you have 2 beams going like this, they are not interacting at all. I need to have an interaction between the 2 physically. So here I am looking at plane waves. So it's approximation in the sense that it's a plane wave. So it's a huge wave. Everywhere they are overlapping. I can't have 2 plane waves which are not overlapping, because they are infinite extent. Okay. So let me put some numbers and calculate what kind of efficiencies the gain coefficient we will get. So the gain coefficient is given here. So let me take a typical example. So here's an example where my incident lambda corresponds to 1 micrometer. This is the corresponding to omega frequency. Okay, we take lithium niobate, 30 10 to the minus 12 meters per volt. We need the refractive index, about 2.2 is the extraordinary index of lithium niobate. Let me take a power of 1 watt, and let me take an area of 0.1 millimeter square. So let me substitute these numbers into this equation. So the gain coefficient will be so you have in this equation, you have everything. You have omega from this wavelength, you have the d, you have velocity of light in free space, n1 is known, s is known, c mu 0 and p2, everything is known. So if you substitute here, what you get is this is about what units will it have? 1 by length. It is exponential kappa u, right? This is the gain coefficient, so it's actually in meter inverse. That's not a large gain coefficient, because suppose I take a crystal of length 5 centimeters. So by what factor will the power increase at the output? Sorry? No, not E. Here's the gain coefficient, length is 5 centimeters. E to the power 10 times 0.05, which is 10 e to the power 0.5, which is about 1.6. E is about 2.7, so 1.62 or something like that it is. So it's only 60% increase of power in a length of 5 centimeters. If you compare this with a amplifier with simulated inversion, population inversion, these are very, very small. A semiconductor laser has a very huge gain in thousands of meter inverse because of population inversion. So as an amplifier, this is not very, very interesting. But remember, if I put this amplifier within a laser cavity, between a pair of mirrors, I can convert the amplifier to an oscillator. You have studied lasers in some course. So I take this amplifier, put a pair of mirrors on either side of the amplifier. The stimulated emission that happens, the spontaneously generated light can reflect back and forth inside the cavity, and as it propagates, it gets amplified, and you can form what is called as an optical parametric oscillator. This is an optical parametric amplifier where you have input signal getting amplified. There you have an oscillator in which you don't put anything from outside except for the 2 omega beam. You need to put the 2 omega beam. So you can build an optical parametric oscillator, which we will discuss a little later, by taking this amplifier and putting between a pair of mirrors. So I have 2 omega coming in from here, and omega gets generated inside, and I get omega coming out. The 2 omega passes through these mirrors. I could have different situations are possible, so we will look at these. This is called the OPO, optical parametric oscillator. This is one of the very important tunable lasers available in the market. It's tunable because I can actually, as I will show you later on, I can change the phase matching condition and get different frequencies coming out from here. So this will become a little more clearer as we go to interaction with 3 different waves, 3 different frequencies. Here we are only looking at 2 different frequencies, omega and 2 omega. So in general, I can have omega 1, omega 2, omega 3, 3 waves interacting, and I'll show you that this is a very interesting source of coherent radiation because I can actually have a tunable output coming out from here. So I can start with a visible laser here and come out with infrared lasers tunable over a very broad range of wavelengths. So although the amplification is small, this interesting property of this amplifier is that, as I will show you later again, that for an amplifier, a very important property of an amplifier is the noise added by the amplifier. Every amplifier adds noise, which means if you have a signal coming into an amplifier containing some noise, that amplifier will amplify the signal, will amplify the noise input, and will also add its own noise. So usually the signal to noise ratio, which is a very important property, at the output is always worse than at the input, because you have a certain signal and noise, both of them get amplified by the same amount, and then you also have a noise generated by the amplifier itself. So this is a very important property of all amplifiers, the change in the signal to noise ratio by the amplifier, and as I will show you later, that this amplifier can operate in a region where it does not add any noise to the signal. So it can act like a noise-free amplifier, and that's very interesting for many applications where in many times your signals are very weak, and if you want to amplify it without adding noise, that's very interesting. Any weak signal, if you try to amplify, that weak signal could be comparable to the noise levels, and you will be worse off by amplifying than without amplifying. So this is a very important property of this amplifier. Other than that, these amplifiers are very important for making an oscillator. Okay. Before we move on to further discussion on 3-wave interaction, what I would like to do is briefly present one interesting aspect which we have a brief heuristic derivation of something which is very important. Remember, if I go back and look at the expression for efficiency for second harmonic, when we neglected depletion of the second harmonic. If you remember, we had obtained this equation, eta is equal to 2 omega square d square mu 0 by c n1 square n2 p1 by a L square into sine square delta k L by 2 by delta k L by 2. So what I've done is I multiplied and divided by L square, keep this as a sinc function, and there's an L square here. So there is a efficiency dependence on L square, and this is assumed, this is derived assuming that the omega wave and the 2 omega wave are plane waves. It also shows me that I can increase the efficiency by increasing P1 by A, which means for the same power of the fundamental, I can increase the efficiency by focusing the beam at omega frequency. I can reduce the cross-sectional area of the omega frequency. So let me try to approximately use this equation and try to estimate, should I too much focus or should I less focus? What should I do? So for this, let me assume that I have a Gaussian beam. Usually the laser beams have a Gaussian transverse distribution. So I have a Gaussian beam which I try to focus into the crystal. So here's my crystal. The omega beam comes in. There's a lens here which focuses the omega beam into the crystal. So this is the base size of the Gaussian beam, W0. Remember, we had I had given this formula right at the beginning. The 1 by E width of the Gaussian beam changes with Z according to this equation. This line, actually, this line which I'm drawing is the distance from the axis where the amplitude reduces by a factor of E. So the Gaussian beam has a variation like this, exponential minus x square plus y square by W0 square. The electric field of the, this is, sorry, I must write this. This is at the input at Z is equal to 0 at the waist. And at any other value, it goes as exponential minus x square plus y square by W square of Z. Okay. So this is a Gaussian beam which is getting focused and expanding from the crystal. So what I need to do is, so remember here that if I try to I think my hand touches that. Okay. So the so this is the change of the size of the beam, area of cross. This W is the radius over which the most of the Gaussian beam is amplitude is present. So you have a beam coming like this. You focus it, goes down and comes up like this, and this W0 or W of Z defines this distance. So the cross-sectional area is so much here, the cross-sectional area is so much here, the cross-sectional area is so much here. The beam starts with a large cross-sectional area, becomes focused and comes out. Now for Gaussian beams, I can define a distance where W changes by a factor of √2. What is that distance? From this formula, when Z becomes equal to, when this quantity becomes 1, then W increases by a factor of √2. So this is called the Rayleigh range. So this distance is equal to pi W0 square by lambda. When you choose a distance is equal to pi W0 square by lambda, then W of Z at that point is √2 times W0. So I can approximately say that the beam maintains its cross section over a distance of the order of ZR. Beyond ZR, the spot size of the beam becomes more than √2 times W0. Now, in a focused beam like this, the intensity is varying as a function of Z. In a plane wave, the intensity of the fundamental does not vary with Z because it is not getting focused. Here the beam is getting focused, so the intensity starts from some value here, maximum at this point, and then starts to decrease again here. So I can approximately define a distance 2 times ZR. That means from this value to this value, this is the distance over which the beam will maintain its approximate cross section. It is not exactly W0 all the way, but it is W0 here, it is √2 times W0 here, √2 times W0 here. So I can approximately say that if I use a crystal of length 2 ZR and W0 is the spot size of at the base of the Gaussian beam, then I can achieve an efficiency assuming that the intensity remains almost constant across this length. So unlike a plane wave where I can choose arbitrarily A and L, here for a chosen value of A, the area of cross section, L gets fixed. Because if I choose a certain W0 value, the ZR value gets fixed because of W0 and the wavelength. If I choose a smaller W0, that means I focus more, ZR will reduce. If I focus less, I can have a longer length of interaction. So the length of interaction and the area of cross section of the beam then get coupled to each other. They are not independent quantities now. So I can use this equation approximate that L is 2 times ZR. The length of interaction can be assumed to be 2 times ZR, and the area of cross section A is equal to pi W0 square. So this quantity L by A, which appears in this equation, becomes equal to L by A. So L is 2 ZR by A is pi W0 square, which is equal to 2 times 2 by lambda, because of this equation here. ZR is pi W0 square by lambda. So L by A is 2 divided by the wavelength of the incident wave. This is assuming that the length over which I am interacting is approximately twice the Rayleigh range, where the spot size goes from √2 times W0, starts from √2 times W0, becomes W0 here, and becomes √2 times W0. So if you now use this equation for L by A, what you see immediately is eta becomes equal to 2 omega square d square mu 0 by C n1 square n2 P1. L by A is 2 by lambda into L into this sinc function, sinc square of delta K L by . So what you find is, when you are phase matched with plane waves, the efficiency increases quadratically with length of interaction. If you double the length of interaction, you will have 4 times the intensity, 4 times the efficiency. But in actual practice, when you try to focus the beam, the efficiency does not increase as L square, it increases as L. Because you need to worry about the fact that if you try to decrease the area of cross section, the length of interaction will also reduce automatically. Your crystal may be very long, but beyond a certain length, the intensities are too low for efficient conversion. So this is a sort of an approximate derivation or approximate estimation of what will happen to the efficiency if I were to use a focused beam rather than a plane wave. So in a plane wave, the efficiency goes quadratically with length for phase matched interaction. For a focused beam, the efficiency actually goes down. It only increases as a function of length, proportional to length. So if you double the length with a focused beam, keeping in mind that this focusing and the length are related to each other, you will have only double the efficiency, not 4 times the efficiency. So this is always to be considered when focusing beams, because the efficiency of nonlinear interactions is proportional to the intensity of the incident wave, not the power, the intensity of the incident wave. And to increase the intensity, you may try to focus, and if you try to focus, you are restricting the length of the interaction process. Okay, so I thought this is an interesting aspect which we have not derived rigorously, but we have just estimated from the plane wave expression. We have sort of used an approximation and tried to estimate what will happen if I have a Gaussian beam instead of a plane wave. Okay, so do you have any questions till now? What we will do is, after this, we will move into a 3-wave interaction process. I will just introduce this today and in the tomorrow's class before we go on to minors. Yeah, any questions? I had left a problem of calculating the bandwidth of interaction. Did any of you try it out? Yes. There is a problem with the tutorial sheet on the sheet also with numbers, but to be able to obtain an expression for the bandwidth of interaction process.
Lambda omega by 2 is?
No, no. You have to worry about dispersion, dn by d omega. Please work it out again, otherwise we will discuss in the class. Okay, the problem is that if I look at this interaction process, if I look at this efficiency, at delta k is equal to 0, I have maximum efficiency, and as delta k changes, the efficiency drops down. Remember, we had plotted this figure as a function of delta k. So I have, if I plot eta versus delta k, I'll get a sinc function like this. So what is the value of this? What is the value of delta k where the efficiency goes to 0? Delta k L by 2 is pi, which is, this is 2 pi by L, and this is minus 2 pi by L. So, which means that at delta k is equal to 0, eta is maximum, and this corresponds to what? One particular omega value. Some omega value for which n of omega is equal to n of 2 omega. Now, if delta k is equal to 2 pi by L, the efficiency becomes 0. So, to what omega does this correspond? That's the question. Which means I have this crystal, I have omega here, tunable laser. So, if I choose an omega, let me call this omega naught. If I choose an omega is equal to omega naught, for which n of omega naught is n of 2 omega naught, I have delta k is equal to 0 and I have maximum efficiency. Now, I change my frequency from omega naught slightly away from omega naught. As I start to change my omega from omega naught, n of omega and n of 2 omega will vary, and this condition will no more be satisfied. And when this condition is not satisfied, delta k becomes finite. And when delta k value becomes equal to 2 pi by L for a given length of interaction, at that frequency, the efficiency will become 0. So the question is, what is the change in frequency required from the center frequency for the efficiency to drop to 0? That means, how precisely should I adjust this omega frequency for maximum efficiency? This is actually contained in the last problem here also, with actually taking into numbers, because we have this, I've given the Salamé equations defining the refractive indices of the crystal as a function of wavelength. So, but what would be interesting is to obtain an analytical expression for delta omega. What is the delta omega for which delta k is equal to 2 pi by L? Because delta k is k2 minus 2 k1. So this is k of 2 omega minus 2 of k of omega. So what is the shift from omega naught that I need to have for the efficiency to drop to 0, when that means what is the change in omega for which delta k, the corresponding delta k, becomes 2 pi by L, and that will give me the bandwidth. And this is very important because when I try to perform an experiment, I would need to know to what precision I need to maintain omega. So if omega changes by this value corresponding to delta omega, the efficiency drops to almost 0. Okay, so that's the bandwidth of interaction, and that I would like you to sort of calculate and obtain an expression for delta omega, and let me tell you, it will contain the derivatives, because you will have to make some Taylor expansion of n of omega around omega naught.
If we assume delta omega to be very small, we can sustain with only one term.
Yeah, but you need to get a delta omega value.
If we assume that delta omega is very small as compared to omega.
Yes, you will assume. Yes, agreed. N of omega will be equal to n of omega naught plus delta omega. So this is n of omega naught plus delta omega dn by d omega. Plus you keep the next term and find out whether I need to keep it. I wrote a check. Similarly, I need to do for the second harmonic at the second frequency.
Yeah,
and then
when we take the difference, how the terms will cancel.
Yeah, so I leave it to you. So this is what I leave the problem to you to solve it out. Any question? Okay, let me just briefly introduce this this other process, and we will do the mathematics the next class. So the problem is the following: that now I have omega 1 and omega 2 incident. Two waves at two frequencies are incident on the crystal. Remember, nonlinear polarization is 2 epsilon 0 d e square. Now I'll get back to the scalar equation, because as I showed you, I can always obtain a scalar equation which I can obtain from knowing the polarization states of the waves and the crystal d tensor, etc., etc. So I don't have to actually solve the equations with the complete tensor notation. I've sort of approximated by scalar equation. Now, can you tell me what frequencies can come out from this interaction process? So what can exist at the output? 2 omega 1 can come out, 2 omega 2 can come out, second harmonic of omega 1, second harmonic of omega 2, and then plus omega 2 and mod of omega 1. Right? That's the only possible output. Now, what will determine what frequencies will come out? Will all of them come out, or only some of them come out, or what will determine which comes out? Phase matching condition. So, for example, to generate omega 1 minus omega 2, what is the phase matching condition I need to generate? I need to satisfy. So, let me assume that this is omega 1 is bigger than omega 2. Let me assume omega 1 is bigger than omega 2. So, this is omega 1 minus omega 2. So, to generate omega 1 minus omega 2, which I call as the difference frequency. So, what is the propagation? What is the phase matching I need to satisfy? K1 minus K2 is equal to the difference in propagation constants, because you will see when you substitute here and you get the nonlinear polarization velocity. Remember, I had one quiz. The velocity of the nonlinear polarization becomes equal to the velocity of the electromagnetic wave at omega t when you satisfy this condition. So this is for difference frequency generation. If you choose K1 plus K2 is equal to Ks, where Ks is the propagation constant corresponding to this frequency, then you will generate some frequency generation. And of course, if you satisfy the corresponding second harmonic generation conditions for omega 1 and omega 2, you will get the second harmonic of omega 1 or second harmonic of omega 2. Now, in normal practice, it is not possible to satisfy all these conditions simultaneously for the same set of frequencies at the input. So, you will generate one of these processes or none of these processes. You may not satisfy any of the phase matching condition. Your omega 1, omega 2 incident, outcomes omega 1 and omega 2, nothing else. So, what we will study is this process in which I have two waves incident, and generating a third wave. Now, to be more specific, we will call these by the following names. So, I will assume that the three frequencies are satisfying this condition. So, P stands for pump, S stands for signal, and I stands for idler. Instead of taking omega 1 minus omega 2, omega 1 plus omega 2, whatever it is, I will have three frequencies. They are defined such that omega s plus omega I is equal to omega p. So, if I want to look at some frequency generation, I will assume the incidence of omega s and omega I to generate omega p. This is some frequency. If I want to look at difference frequency generation, I will have omega p and omega s or omega I generating omega I, and this is difference frequency. So, omega I here is equal to omega p minus omega s, and omega p here is the same equation, omega s plus omega I. This is just to make it a little self-consistent. Otherwise, what will happen is, if I give you omega 1 and omega 2, if I generate difference frequency, I must call it omega d. If I generate some frequency, I must call it omega s, etc., etc. So, just to avoid this confusion, the three frequencies which you will consider are always related through this equation. Omega p is equal to omega s plus omega I. If I want to look at some frequency, the input waves will be called omega s, omega I. If I want to look at difference frequency, I will call them omega p, omega s. So, if omega s becomes equal to omega I come back to the old process of second harmonic generation and the subharmonic generation. Because if these two become equal, omega p becomes twice omega s, and that is corresponding to second harmonic. This will then correspond to second harmonic generation, and this will correspond to the parametric tone conversion. In general, omega s and omega I are different. All I need them to satisfy is their sum must be equal to omega p. And all these processes will require the following phase matching condition: Kp is equal to Ks plus Ki. That means the propagation constant at the pump frequency must be equal to the propagation constant at the signal frequency plus the propagation constant at the idler frequency. I can actually generalize this to quasi phase matching, which I will come to little later. But so what we would like to do now next time is to derive equations relating the electric field amplitudes at omega p, omega s and omega I. Till now we have had two equations corresponding to omega and 2 omega. Now we will have three equations, one corresponding to omega p, one omega s and one for omega I. So depending on the process which I want to study, I will pick up those two equations. Assume the third one to be undepleted. For example, here I will assume usually that omega p, that's why it's called pump, is a very strong electric field, and this is a weak electric field, and this generates omega I, or both of them are strong. So omega p is very strong, so the electric field at omega p will be assumed to be constant in solving those equations. If I look at this equation, I will assume one of this, omega s will be very strong and omega I will be very weak, and I will assume the electric field at omega s does not vary with z and neglect that equation. So I can use those three equations to solve any of these problems. So these are all the nonlinear processes that you can generate with these three waves. This is called three-wave interaction. There are three waves interacting to form all the nonlinear processes. This process is used, for example, to convert light at infrared frequencies to visible. This frequency is higher than this frequency. So suppose I have a signal coming at 2 micron wavelength. I can mix the 2 micron wavelength with, say, 600 nanometer wavelength to convert this to a new frequency which is very close to 600 nanometers. So at 2 micron, I may not have good detectors. I have good detectors at the visible wavelength, so I can have a very interesting detector by using some frequency generation. I increase the frequency of the signal from 2 microns to 1 micron or half a micron, and I have good detectors. Silicon detectors are very good, very efficient in the visible region. This is used to generate infrared from visible, and this is what will be used for parametric amplifier and parametric oscillator. In fact, I'll show you here these three equations that the omega s signal gets amplified in this process. So we will derive these three equations and solve these three equations in the next class. Okay, so do you have any questions? Okay, thank you.